And I will say what most people probably would not say because I'm not afraid to say it. I think we really need to accept the fact that we have equivalent capability out there to our own, or maybe have even been surpassed in some ways because we've been arrogant as Western society that we'd always have the dominant position on orbit. And we don't have the dominant position on orbit anymore.
Space is really the backbone of so much of our current world and economy.
I think the holy grail of the future really is, in my lifetime, nuclear thermal propulsion.
And the only way the science fiction future happens is if we make it happen.
Welcome to the Long Frontier podcast. My name is Brannon Jones. I'm co-hosting with Abe Murray, and we are going to talk about the technologies that are going to shape the next 30 years of human civilization. Today, we are going to do our first episode on the final frontier, aka space. This is a topic that's near and dear to my heart, and also near and dear to your life, even though you may not know it. A lot of people think about launch and SpaceX, but that's not all there is. That's not all that there will be. And so we're going to dive deep into that. But hey, before we do that, why don't we actually, Abe, you want to introduce yourself and then I'll go?
Yeah, I love it. Well, thank you, Brannon. It's a ton of fun to be here. This is a new idea we had, which is, hey, we go deep on stuff. Why don't we share it with the folks we talk to? So I'm Abe. I'm here at AliCorp. We're an early stage investor. We invest in, pre-seed and seed deals. Deep tech to us means aerospace, space, energy, manufacturing, robotics, and more. We've been doing this for a bit. And I got into it, as a high school dropout who ran some fishing boats and factories, saw his way around the real world, and then went back to school for engineering and built some stuff that's space adjacent. Worked in aerospace for a while, working on unmanned aerial vehicles. Some of them flew very high in the sky near the edge of space, doing electronic warfare up there. Now, Brannon and I are lucky enough to invest right at that edge, making it happen in the future. It's a ton of fun.
Man, and I love doing this with you. We love the science, and that's honestly why we are doing this podcast, as an ode to all of these builders and founders and inventors and all the investors who are making the ecosystem happen. This is our little way to give back. My name is Brannon. I'm a venture capitalist alongside Abe Murray at AliCorp. I also focus on deep tech with him. My background's mechanical and aerospace engineering, specialized in robotics and electric propulsion. Specifically, I was working on applied field magnetoplasma dynamic thrusters. For those who are interested, we'll talk a little bit about that today. Then I did some time at SpaceX. I was on Falcon in the early days of reuse, crawling inside the rocket barrels, chopping things out and inspecting them by eye and saying, can this fly again? And if it could, we'd weld them back in. And then I jumped over to Raptor, the R&D side, which is the novel next-gen propulsion system, which has really set the standard in the industry for full flow stage combustion engines, which is the cream of the crop for combustion propulsion systems. That doesn't make sense now. It will by the end of this episode. Let's just jump straight into the episode, Abe. I'm super pumped to do this. I think maybe a good place for us to start is just giving an overview of what is the space industry. And most people see launch services. They see SpaceX and Blue Origin and Artemis and all these things going up. And they think that's the whole thing. But actually, space is really the backbone of so much of our current world and economy. You have communications and connectivity. That's a $100 billion market of satellite services, broadband included. Starlink is 10,000 satellites up there of the total, 15 to 20,000 satellites. But there's a bunch of others. And that's only going to grow 3.4 to 4 billion. Half the people on the world don't have cell service and connectivity. So you have to imagine that keeps growing, and it's already a major thing. Earth observation is probably another $10 billion market. It's kind of funny because most of the things we send out to the final frontier at space, we basically just turn it around and look back at ourselves. But that still is critically important. There are hundreds, thousands of satellites up there that are looking back at us. And that's super important for commodity trading, for insurance, flood assessment, and agriculture uses that a ton. That will continue to only grow as well.
I was going to say, what's crazy about that is GPS was the thing, but now Starlink does it magically and better with many more satellites. And in fact, I just read an article that people are using not even getting signals from Starlink, but like watching them move across the sky to do finer grained GPS analysis, effectively location on the Earth. It's kind of wild. Everything's changing and we're barely paying attention. We just think GPS, but actually there's so much stuff up there. The phones we hold can reach up into space and see things going on up there and think about it. It's just starting to change the world.
Honestly, that is not so surprising. I mean, GPS is 31 satellites that have atomic clocks that were launched in the 1970s. So it probably is time for some new innovation. That is crazy just to think about how much people are doing in Starlink, doing the direct to cell, and people's innovation in finding cell phone signals just from looking at what's up there already.
And then defense, we're spending probably $50 billion on that we know of, that's reported publicly. And there's always been a big defense angle to space, but we can only expect that gets bigger over time. Certainly as the U.S., with the U.S. Space Force pays more attention to it, and we imagine that this plays out across the rest of the world as well. So all of that adds up to like 600 billion. Is that the number? Something like that, depending on the report.
I think they're conservative, but that's the number.
Yeah. So if you call up your best friends at the fancy places like McKinsey and say, how big is this thing going to get? They're going to say, it's going to be like twice as big, maybe 1.2, maybe 1.5 trillion, maybe 2 trillion.
It's a big number.
It's a big number, but we had Pablo Holman on stage at Deep Tech New York earlier this year, and he was talking to the deep tech audience, and he was like, look, all of tech, all of venture gets so excited about like a $3-5 trillion software market, which by the way is a bigger number than what McKinsey thinks space will be. Pablo's point was actually the global market, the economy, the real economy is like 100 plus trillion. It's big. And the things we think about as tech are tiny. And we need to think bigger as technologists about like solving the big problems humanity faces. So that's like one idea to hold in your head is the market's much bigger than even most of us think about day to day. And two, those same smart folks you call up, somebody called them up like 20 years ago and said, how many smartphones are there going to be? And they did their hard thinking and they came up with a big number. There's going to be 1 million smartphones. That's how big the smartphone market's going to be. So when I think about the predictions for what's going to happen here, I just go back to humans are terrible at exponentials. We cannot understand how things change when they're changing fast. And I think access to space is an exponential that's going to change what happens up there. So that 600 billion mark is big. It's more than launched. That blew my mind. When you taught me that fact, blew my mind. I didn't believe it. It's true.
But I am hearing your point, and I do think our predictions are still way too small. I mean, it could be 10 times bigger than that easily. And we are seeing, in my opinion, all of the precursor elements come together so well to actually catalyze an even much bigger market. I love that. I love that analogy with the cell phone market. But I mean, you look at launch costs have fallen dramatically. If we were trying to put something into low Earth orbit using the space shuttle in the 1980s, it probably cost us $65,000 per kilogram of mass that we send up there. If you want to use Falcon 9, Falcon Heavy, it's $1,500. So we're already talking about a 40x reduction. And Starship plans to cut that in half or in a quarter. Like easily, launch costs could have come down 100x in the last 40 years.
And we all just heard Elon in a latest pod saying he wants to chuck a couple rockets into space every day. So he just dreams bigger dreams all the time. And the exact year that happens might shift, but that's going to happen, right? We know that's the future. So we're early, not because nothing's happening, but because everything has yet to happen. There's so much that will happen. And that's something that you really held in your head when you and I started investing and looking at the space and thinking broadly about what should we be doing in space. And it was our observation that everything's going to change when costs come down to get stuff up there. And then everything's going to change about what happens up there. So today you said there's 15, 20,000 satellites, things up there. Sounds like a lot, but it's tiny compared to the amount of stuff on the surface of the Earth, the number of cars, the number of buildings, the number of boats, the number of cell phones, like whatever it is. We measure things in the billions down here, and we're measuring in thousands up there. So that's going to shift. So what happens when we put more stuff up there? Like, what does that mean? What do you think about wearing your space hat?
Yeah, right. It's a great point. You're right. 15, 20,000 things. In 2014, there was maybe 1,000. So even already we've seen 10, 20x. And people think there's going to be 100,000. Although, granted, it's the same McKinsey folks, so maybe they're off by still an order of magnitude.
I'm going to guess 1 million, 1 billion. Like, if we just keep doing the right things as humanity, that number should get as big as you can imagine and then bigger.
I think you're totally right. But if you put that many satellites into low Earth orbit, to the point that you were saying before, you're going to need to give those satellites some ability to move around. And that happens that's needed for a variety of reasons. I mean, actually, all satellites have some limited amount of ability to move around right now, just to keep their orbit stable. So if you're fighting lunar gravity, solar gravity, or a little bit of atmospheric drag, if you're close to the Earth, you'll rotate, your orbit will change. So you need to be able to adjust for that. But what we're talking about is like collision avoidance and services layer. And that is just going to become a huge issue in the orbital economy if there are not improved propulsive systems on orbit. Just going on a little bit longer on this, but just to give you some frame of reference, the objects in space and low Earth orbit are moving at about 17,000 miles an hour. And so and that's just one way. So if they collide with something, and if that something is moving the opposite way, it could be like a 20,000 mile per hour impact.
That sounds bad.
It sounds bad. It's already 10 or 15 times faster than a bullet. But then if you think about how kinetic energy is 1/2 mass times velocity squared, the energy increases to the square of velocity. That means you're actually like 10 to the second or 15 to the second. So 100 or 200 times more kinetic energy than a bullet.
I'm impressed by the public math, but again, I'll go back to, it sounds bad.
It sounds bad.
Probably shouldn't hit things.
There are stories of paint flecks that hit the windows of the ISS so bad that they have to regularly replace them. And they're that small. They're smaller than like a centimeter. And we can't see anything that's under 10 centimeters in space. So right now, people just have like a probabilistic like plan that their satellite's not going to get just demolished on orbit and say, well, probably nothing will hit it. But if it does hit it, that's it. So,
some people hear us talking about this and think, hey, Brannon, hey, you guys are crazy. You want to put a lot of stuff up there. It's already crowded. Yeah. We don't want to pollute space. And again, with my layman's understanding, the majority of things are down in low Earth orbit. There's a ton of space up there. Like, space is big. It's a cliche. It's really big. Yeah. And then problems in low Earth orbit, as I understand it, they solve themselves. They kind of fall into the Earth's atmosphere and burn up and dissipate. So yes, we want to move things, but mostly you just need to be able to move a little bit and it's okay. And we can put a lot more up there. Is that a correct understanding?
No, that's actually a very correct understanding. And there's two things I would say to that. The first is that the FCC, part of the Space Bureau, actually, I think it was in 2020 or 2022, made a rule that you have to deorbit your stuff after 5 years, which SpaceX was a huge proponent of this because now it means the people have to pay them again every 5 years to put their satellite back up there. But their whole idea was exactly what you're saying. There needs to be some regular deorbiting because people haven't really built the infrastructure for things to just stay out there. And that goes to my second point, which is you have to imagine that as the orbital regime gets more and more full, we're actually going to need to service those. We'll need to refuel them. We will need to move them. We will need to deorbit the ones that are broken or defunct or just outdated. And we will need to deorbit the space trash of the ones that had a collision and blew up. So all of this is going to matter. And we will need the on-orbit capability to see that debris coming at us earlier and move around it. Because again, right now we can't see less than, call it 10 centimeters right now because we just look from the ground. So there's this whole space domain awareness push right now on the technology side where people are trying to put sensors on satellites so that while they're in space, they can see something that's coming. They can use a much higher resolution sensor and they can move so that they're not getting hit by paint flecks or whatever else would just take out a satellite. So
and that goes back to the airports, no roads analogy. We figured out how to fly stuff up to space.
Yeah.
We haven't figured out how to drive it around once we get there in a meaningful way.
Well,
and we certainly haven't built, the tugboats, the, fix-it trucks, the depots, the things that are going to go manage all of that. That's all yet to come.
That is, And it's coming. It's coming. I was looking at a cool stat. I was chatting with a founder actually who told me this. And they were saying if you were to look at the cost of rocket engines and propulsion systems for satellites, you would basically see that 10 years ago, the cost of like dollar per pound of thrust that the engine could actually create, it's like $300. Right now, thanks to innovations in Raptor and electric propulsion, all these other things, it's about $1.50. So it's like a 200x reduction in the cost of propulsive systems. To your point, I mean, that hasn't quite gotten out there yet, but it is the fundamental breakthrough that you need to start seeing the kind of innovation and explosion of propulsive systems that are required to do all of the mobility things that we're just talking about in space. So it is absolutely coming. And there is more innovation on the forefront of propulsion, which it's just now becoming a problem that people care about because the cost has fallen, the technology is improved.
What's made the cost fall, right? Besides launch costs, which we all understand, right? Big rockets get better. What else is getting better with our ability to do things up in space?
Yeah, that's a great point. I think a lot of the reason why the costs have fallen is because people now realize that it makes sense to do things in space, that there can be an economy there and there's more focus on it. So my days in Raptor, I think Raptor has been a great example of a way to, of a program that has demonstrated this dramatic drop in cost. And the way that we did that was through vertical integration. The way that we did that was through rapid iteration, all the things people say about SpaceX, but it really was like simplifying the technology and just trying to reuse it and finding out what actually does work. There are many times where we'd fly something and we'd say, okay, that engine looks like toast, but can we fly it again? How toasty is it? We'd take them apart. We had a whole section of relegated engines where we would pull them off, swap parts out, try to get them back together and find something that was working. So we understood, well, one, have we designed this well? Have we designed it in a rugged way? Which pieces did last? Is there any margin to shave those things out of there? And then two, figure out kind of what could we, of the parts that didn't last, what could we internalize into the vehicle and simplify it? So I do think in many ways, SpaceX's focus on propulsion has led the way, but it's kind of the existence proof thing. People see that SpaceX is doing it. People see that propulsive costs are falling and more people want to be involved. So there's much more science around these different kinds of propulsion. And actually, my background is in electric propulsion. 10 years ago, well, I guess more than 10 years ago, I was working on magnetoplasma-dynamic thrusters, applied field magnetoplasma-dynamic thrusters at Princeton. Bunch of word salad, which just means you're using an electric field to shoot out metal ions out of the back of your electric thruster. And we were saying, this is going to be the best propulsion system because you get really high efficiency and high speeds out the back. And you get high thrust because if you're shooting out an entire ball of metal, you're going to get more thrust than if you're shooting out one single plasma ion, which is mostly how electric propulsion works right now. The only catch was that you needed 200 kilowatts of power on orbit, which right now vehicles only have like 60 kilowatts. The whole ISS generates 270 kilowatts, and it's a massive structure. So have 200 kilowatts on a tiny little satellite. We're like, it's going to be ready in the next 10 years. Now I'm telling you, it will be ready 10 years from today. So anyway, all that to say, there's so much innovation coming on that forefront. And I think we have a great guest today that I want to invite to help us explore what actually is going on in the propulsion research world. What are the cutting edge solutions? What's going to come to market? And how is it all going to work? All right. So now I would love to welcome into our conversation none other than Jeff Thornburg. He is an aerospace propulsion expert. He's got 30 years in the industry. He spent time at NASA. He spent time at SpaceX. He's been in the defense world. He was kind of one of the chief architects around the design of the Raptor engine. So Jeff knows exactly what he's talking about. We're going to walk through the fundamental physics of how we move things around in space with Jeff. Jeff, I will let you say anything else before we jump right into the details.
No, I like it, Brannon. You're a great hype man. I think you nailed it on the head there.
All right, great. Well, we've been talking a lot about why we need to move things around in space. Why now is the time? Why now it's possible? We want to dig into the how we do it. And so, just if you can help us set the stage, how do most satellites move around on orbit? Like, just kind of what's the default?
There's two methods in which we move spacecraft on orbit. One is where, as some in the audience may understand, when you're orbiting a planet or the Earth, you're essentially falling around the Earth in a big circle. And so, one way you move spacecraft is you orient it so that you can take pictures of things on the ground or in space. You normally do that with something like gyroscopes are called reaction wheels, and they allow you to tilt the spacecraft. Or you might use tiny thrusters to change the tilt so that your camera or whatever you're using to observe something can move and track an object. But if you actually want to move a spacecraft between orbits, then you're going to use a propulsion system to do that. And there's various ways to do that. And when you say propulsion system, you're really just using a device that throws mass out a nozzle, and action reaction force, thank you, Isaac Newton, allows you to then propel your spacecraft either faster forward or in reverse and deorbit. Or so there's two ways to go in orbit. Typically, you're either going higher in altitude or lower in altitude, or shifting how you're tracking the Earth. So those are kind of the basics, fundamentals. I'm happy to talk about kind of not get too mathematic or geeky about it, but actually how that works and how those.
No, let's get mathematic and geeky about it, because I think a lot of people don't even realize that there's a reason to move between orbits. And you also, failed to mention, you were the CEO and CTO of Portal Space. You have staked your whole business on the idea that people need to do this. So tell us a little bit also about that. Why are people even moving orbits?
Well, lots of questions rolled up in there, but I guess what I'd say is until about 5 to 10 years ago, we didn't really have the capability to launch very quickly, rapidly, or cost effectively into low Earth orbit. And when I say low Earth orbit, you're talking about roughly 200 to 500 kilometers above the Earth's surface. And so it didn't really matter a whole lot to find different ways to move on orbit with new types of spacecraft, because it was so costly and time consuming just to get spacecraft onto orbit because the launch costs were so high. So this was the domain of nation states. So the United States, Soviet Union, now Russia, now China joining the party, and then a few other nations, the European Union, Japan, kind of joining the launch capability market. But the costs were so extreme, it was tough just to get up there. And that's why things were so slow and so expensive in terms of human exploration. But now, in the last decade, we've cracked reusability for launch vehicles, which makes the cost of getting orbit cheaper, which now means we can innovate around new types of spacecraft and missions that weren't possible because you have a cheaper way to get to orbit. So that's why at this point now we're looking for more cost-effective ways to build spacecraft, more cost-effective ways to maneuver those spacecraft. And ultimately, I think it's because our whole economic future is tied to the space domain. And that's the reason why you got to get more clever with how you do these things.
Well, so the way that they are doing these things and what has seemed clever now is really chemical propulsion. When we see people moving from orbits or getting into orbit, it's all been chemical. What are the strengths of that method of chemical propulsion, combustion, and where does it hit a wall? Like, why do we even need to get more clever than what we figured out so far?
Well, I'll take you back to kind of the fundamentals first. So the foundations of this are in an equation that most people have heard of, which is force equals mass times acceleration. Classic Isaac Newton, three laws of motion. And if you do some clever mathematics with calculus, which Newton also invented, you can turn that very simple force equals ma to something called the impulse momentum equation. And what that looks like is you have force over time. So applying, say, a thrust or a force or a push over a certain amount of time is your impulse. And then how you figure that out is a change in velocity. And so how you get that change in velocity is very much tied to something called momentum, which fundamentally momentum, you can think of it as the movement of a mass with a speed or a velocity. And I'm telling you all of this background because ultimately, to thrust something with a propulsion system, it's all about the change in momentum, the mass times velocity. So
And this is the underpinning of the Tsiolkovsky's famous rocket equation. Then is that correct?
You can get there, yes, with the help of calculating delta V, but just fundamentally, when some people may have heard of like a rocket engine is basically you're throwing propellant that's burnt in a liquid engine system out this nozzle system. And the reason why all of this is important is the faster you throw the particles through the nozzle, the more effective the engine system is in terms of both thrust and performance. So when you see a rocket engine ignite on the launch pad, you were seeing molecules and atoms coming out of that plume that are moving on the order of thousands of feet per second type of movement. And so that's how you can have these tiny little molecules be able to thrust this huge rocket that weighs, it's the size of a skyscraper and weighs, 6 or 7 million pounds in terms of like Starship and Starship Booster, because of this effect of velocity. So velocity times the mass of even a small particle leads up to a large figure. So that's ultimately in physics how the nature of a rocket engine works. And so if you stayed with me through all of that, it gets to your question of different types of propulsion systems. All a propulsion system does is it changes the energy of a system to allow you to move forward. So with chemical, you burn a fuel with an oxidizer or oxygen, and it rearranges the chemical bonds of those constituents.
Yeah.
And then it throws those atoms out the back of the nozzle. And so the combustion process changes the chemical energy in your fuel into kinetic energy out the nozzle. Movement is the kinetic energy, and that is tied to the momentum discussion we had earlier. With other types, you can still have that same effect by just heating up a fuel and then ejecting it out a nozzle. And then you have electric propulsion that takes ions and accelerates them through electromagnetism and then ejects them with a velocity. So every propulsion system that you see on a spacecraft is basically ejecting particles with a rapid speed to give you a thrust that allows you to move. And which one you pick will decide how much performance and efficiency and overall speed of movement that you'll get out of those systems.
So is there a holy grail of these different architectures that you would pick? Is there one that you would pick in every single case? Are there major trade-offs with some? Like, I guess the question I'm trying to get at is, do you think there will be a dominant architecture for propulsion systems as people put more satellites into space?
Well, if we use launch vehicles as an example, Wernher von Braun, the godfather of modern rocketry, the physics hasn't changed on how to get off the planet. And it's tied to wanting to have your fuel as compact as possible to get the most amount of thrust to get off the ground and through the atmosphere and up into space. And normally what that looks like is a kerosene-based fuel for your first stage of your rocket and a hydrogen-based fuel for your upper stage. That typically is the most optimized solution. But then when you get into orbit, different missions require different things. And so it's not a one-size-fits-all for a spacecraft, because some systems have certain mission sets where they need, larger or smaller thrust levels. Maybe they need to be more super efficient, and they don't care about how fast they get somewhere. They just want to be efficient. Some people want to be fast and efficient. So it starts to become very customer dependent once you're on orbit. Whereas with a launch vehicle, the physics of getting off the ground and out of our quote unquote gravity well are not changing. They haven't changed. It's all about the mass of the system and having the lowest structural mass of your rocket with the tightest and most compact density of the fuel. So there's a clear winner there, which is why you see Falcon 9 and Falcon Heavy using kerosene in their boost stages.
Yeah.
With methane, you kind of get the middle of the road difference. So if kerosene's the best on the first stage and hydrogen on the second stage, if you use methane on the first and the second stage, you kind of get the same average performance of that kerosene and hydrogen system. So this is why the methane-based rockets with SpaceX and Blue Origin, Relativity, and others are so popular, because now you don't have to have two different fuels, so you can get operational efficiency on the launcher. So I think, yes, to answer your question, there are clear winners that you'll continue to see from a launch vehicle, but I think you're going to see a variety of propulsion systems, because there's defense missions that are special, there's exploration missions that are different. There's other types of things out there from a commercial standpoint. So I think you'll still see this variety between electric propulsion, chemical propulsion, and now thermal propulsion, which is the systems we're leveraging going forward.
I would love to hear your take on your thermal propulsion systems too that you guys are using and why you picked it. And I guess my thought on chemical is, but isn't there a fundamental constraint in the amount of energy that you can get out in the ISP you can get? Because fundamentally, the total amount of energy you can get is just what you get from breaking the bonds, and you can't get more than that. With electric propulsion, by contrast, you could just crank that up. If you had enough power on orbit, you could just crank it up to go even faster. So it does seem to me like, will we hit a limit with chemical, and maybe are there other architectures that solve for that? That's one question, and then two is your thoughts on solar thermal and how that fits into this picture.
Yeah, I think we've already hit the limit for liquid propulsion.
Okay.
Even when I started my career 30 years ago, we were already talking about within the Air Force and NASA that we knew the limits of burning kerosene and oxygen, or methane and oxygen, or whatever fuel and oxygen. And it became a game of squeezing out the last, 3% of performance in those systems. That's really the reason. And the reason I say that so confidently is because there's a certain type of liquid engine cycle called full flow stage combustion that really is the pinnacle of specific impulse, which is kind of the gas mileage of a rocket engine and its associated vehicle. And so the reason why SpaceX selected that, the reason why we worked the technology at the Air Force and NASA, was because that would be the ultimate boost level performance for a rocket launcher, to wring out every drop of performance. And now you see SpaceX doing it, you see Stoke doing a full flow engine, you see the Chinese looking at full flow and similar systems. There's a reason why they're doing that, and it becomes a key to not only getting the most performance, but you actually make the environments and some of the components more benign, so you can get reusability and longer life out of the overall component. So I think we're really there on liquid systems. Electric propulsion is interesting because it takes a lot of electrical energy, but doesn't create a lot of thrust. So there's a lot of efficiency with your xenon or krypton or iodine or whatever solution you're looking at for electric. But it tends to be somewhat life limited in the cathode and the anode that they use as a part of the process for a Hall thruster specifically. Sometimes the start transients, how these things start up and shut down and restart, can be life limiting. And so you have some limitations, though we have a lot of long life systems, but they don't get you anywhere very quickly. For things like thermal propulsion, I think the reason why this is so interesting to me is I really wanted to develop systems that could be as simple as possible with the maximum amount of performance to have the longest life of service.
And this is specifically, you're talking about on orbit then?
I am, yeah.
Okay.
Yeah, so I don't think chemical and liquid systems are the right choice for on-orbit solutions. I think electric propulsion is the right solution for certain missions that don't need to move quickly, but want to focus on efficiency. And now there's this third class of propulsion, thermal propulsion, where there's a couple of choices. And to get to your original question, I think the holy grail of the future really is, in my lifetime, nuclear thermal propulsion. And how thermal propulsion works is you're not burning anything, but you're heating up a heat exchanger to a very high temperature, and you're passing a fuel through it. It could be hydrogen, it could be ammonia, it could be a lot of different things, could be methane. And instead of the molecules burning with something, they get hot enough to where they accelerate their energy state, and they actually break their bonds in some cases, just like they would in combustion, and then they shoot out the nozzle very rapidly, like we talked earlier. And this is very attractive because it requires fewer moving parts. And anytime you have fewer parts, your reliability is higher.
You're saying because there's
And
no combustion, you just don't even need to account for that.
that's correct.
Okay.
You basically use, in this case, in the cases that I'm working, you either concentrate solar energy on your heat exchanger to heat it up to a high temperature, or with nuclear thermal propulsion, you use the reaction of the reactor itself to heat up the heat exchanger to a high temperature and pass your fuel through it. It turns out that the hotter you can heat the fuel, the better performance you can get out of the system. You can get extremely high temperatures out of a nuclear reactor. And then it becomes a materials problem where you want to have materials that can handle that thermal type of life and fatigue and be able to transmit that energy to the fuel very effectively.
Yeah.
But I think one of my favorite things about a thermal engine for folks that aren't propulsion people is if you've seen the Back to the Future movie or the sequel, you know that Doc Brown comes back in the DeLorean and he's got Mr. Fusion on the back of the DeLorean and he's dumping banana peels and trash, and that's now the energy. It's not plutonium anymore. The reason I bring that metaphor up is because a thermal engine can theoretically use any fuel and it will still produce thrust.
So this is exactly what I was going to say. It's like almost like you're not even carrying fuel per se, because if you're saying the sun is what's providing the heat energy, that's unlimited in space. This sounds like it changes everything. But go on then.
Yes, it does. So whether you're using the sun or a nuclear reactor, now you can live off the land. So if I have access to ammonia, I can use that in my heat exchanger for my propulsion. If I have hydrogen, if I have methane, and you can design a system where you could literally start to explore the solar system and use the resources that are available to you on the journey that you have. The problem with space exploration right now in operation is you have to take everything with you all in one go. So it's like you're going on a camping trip for 3 weeks and you got to take all the food, all the water, all the clothes, and then you got to carry all your trash with you, and you're lugging this around for 3 weeks. So if anybody goes camping, you understand how painful that whole process could be for 3 weeks. This is how we operate in space. And now we need to start utilizing longer life hardware with resources that exist in the ecosystem. And that could be asteroids. That can be the moons of Jupiter or Saturn. It can be other places. But this is how we will expand our presence in the solar system. You're not going to do it by carrying massive amounts of fuel and oxygen with you. You'll never get the rocket or the spacecraft off the ground or in orbit to really accomplish that with humans.
That's amazing. Okay. And it makes me want to talk about what are some of the reasons why we even need to start to have that more mobility up there, use these new architectures. Where's the early demand coming from? And Abe and I were chatting before, and he was just starting to get a little bit into some of the ties into defense industry. So maybe we'll take it there for next, actually.
Yeah, and Jeff, I'm a child of the 80s. I grew up in Reagan's America. I remember the Strategic Defense Initiative. We were going to have Star Wars, satellites all over space lasers, all this stuff. Spent $30 billion, didn't quite work out. Probably unlocked a bunch of the modern world we live in. But I know that the U.S. Space Force is driving a lot of what's going on in space, and I know you're in the middle of thinking about this. So just love to hear what's different now and what's unlocked now with ideas like yours and what else you see out there.
I think the fundamental difference is not it is technology, but not really fundamentally. I think we now have peer adversaries that can match our capability in space. That's the difference. When we did Star Wars or the SDI, Strategic Defense Initiative program under Reagan, mainly it was a bipolar world. This was mutually assured destruction through nuclear arsenals between the Soviet Union and the United States. And we wanted to dominate space, mainly as a nuclear deterrent, hopefully. And what's different now is we've got multiple nation states that are now peer players on orbit, mainly China and Russia specifically. And they have watched us perform military operations over the last several decades. And ever since the Iraq wars, how we've unlocked capabilities defense-wise on the ground through space application. And they see this, and then they see where we could be weaker, and then also how they want to develop their own space capabilities to dominate. I mean, Iraq and Saddam Hussein never saw Schwarzkopf coming across Iraq because they had no way to see what they were doing. We're operating in a degraded environment in the desert that they didn't think we could operate in, and they had no way to see us coming. Those days are over. I mean, Planet Labs is taking pictures of the globe every 24 hours. People have access to intel they never had access to before. And so we don't have the strategic advantage that we used to have 20 or 30 years ago on orbit. And that's what's really changing the paradigm. And to get to the original question, why is maneuverability important now, or movement on orbit important now? It's because there's a lot more systems up there that, one, the United States and our allies are dependent upon to just survive, our financial systems, our way of life, etc. And we have more adversaries up there that realize that we're vulnerable and want to exploit that vulnerability. And now, in a very Star Trek way of thinking, you can't just float around in orbit and wait until it's convenient to affect something, because by the time it's necessary, it could be over and you could find yourself in a very bad spot. Just look at the Ukraine conflict recently. It's very publicly known that, Russia played games with their space capabilities to be able to degrade what the Ukraine and the West could see and do when they moved across the Donbass region in that part of the world. I'm sure there's probably relevant examples with what's happening in Iran right now as well. Space plays in every military engagement across the board, and it's getting more and more critical because we have peer adversaries. And I will say what most people probably would not say, because I'm not afraid to say it. I think we really need to accept the fact that we have equivalent capability out there to our own, or maybe have even been surpassed in some ways, because we've been arrogant as Western society that we'd always have the dominant position on orbit, and we don't have the dominant position on orbit anymore.
So it's cheaper to get stuff up there now, and you talked about that earlier, and you and Brannon helped make that happen. And it's more important than ever that we do more when we're up there. You can't just have a thing sit up and sit around. When I put on my science fiction hat, the space I imagine is you go up in space and you drive all around like it's a car, and we are just so far from that. So that's kind of the problem you went down to try to figure out how to unpack and change, right?
Yeah, I was inspired for different reasons. I mean, I wanted to see us push human exploration and technology for humanity's benefit farther in my lifetime, maybe fundamentally. And then while I was thinking about that, my friends and colleagues, especially in the defense sector, are agonizing over every military maneuver of spacecraft on orbit. And with the threats that exist today, by the time you wring your hands to try to do something about it, it's done or it's over. We have less and less reaction time to threats that exist. And so we need to speed up our ability to move quickly on orbit to mitigate that problem.
And we see a bunch of money coming into, a modern version of, space defense effectively. And that is predicated upon being able to move these things around. And you're in the middle of that.
Yeah. Absolutely. We don't win a tank battle with tanks that move slow. We don't win an air battle with airplanes that only can fly at one altitude. And we don't win a naval battle with ships that can't move into position and operate quickly. And the space domain is no different. And the further we, push that out there for most of the decision makers to understand, the better off we'll be.
So, okay, maybe final question for you here. But then what does the orbital economy look like in 20 years, given what you've said? I imagine it can't stay the same. Sounds like there's no way it'll be the same. But what does it kind of look like?
Well, I think I'm an optimist by nature, so it's more fun to live life that way, in my opinion. So my optimistic outtake, with a little bit of Midwestern realism thrown in, is that we're so critical on space, and there's somewhat of a gold rush opportunity going forward in terms of the business cases you see with broadband LEO serving whole swaths of the globe and connecting the globe in ways not possible before. One of the best business cases for space. And then I think how that builds out is you've got this data center conversation that's happening now, how that could unfold, power generation on orbit, because obviously we're not going to generate enough electricity the way we do now for the increasing demand of human civilization. And then you've got resources in the asteroid belt. that are attractive. And you've got China running very fast at the moon because there's very attractive minerals and water usage on the south pole of the moon. And I think the first to get there and dominate those resources is going to kind of make the rules for how we operate with the Earth Moon system. And I think, when we get back to really focusing on teamwork and the Western alliances that really have made us great in the past, I think you'll see an uptick in exploration of all those things in service to pushing our influence and reach farther out.
And Jeff, I know we only had limited time today. So as we let you go, I wanted to just ask you anything that we didn't touch on enough, anything that merited a deeper conversation that in your mind is shaping the future or there are massive tailwinds for that we should spend more time talking about or going into?
The thing that pops into my head right away is just the defense angle. The industry is so dependent on defense dollars right now. And I think the next few years of what happens around the globe is going to be so tied to that for so many reasons. There's lots of dimensions to that conversation that might be interesting to an audience. This was great for like level setting people, I think, on why any of this works or is important or what some history is. But I think defense and civil space could both, there could be a focus on both those things that we just didn't have time to do today.
Amazing. Well, thank you so much, Jeff. I know I learned a ton. I'm actually still thinking about a number of the things that you've said, and I do think we will get to that future where space exploration is the reality and makes sense. We can orbit, we can move around on space. We're literally using the sun as fuel. It makes me think of like solar sails. I know we didn't cover that today, but it makes me think of just really an unlock for the future in the most positive way possible. So thank you so much for your time, Jeff. Really appreciate you weighing in here.
Absolutely. My pleasure. Great to see you both as always. And thanks for letting me join.
That was great. Always a pleasure to hear from Jeff.
He's good.
And when we first did this, I had no idea what specific impulse was and any of this stuff. You just think it's some kind of efficiency, but it's a little more complicated than that. So it's actually nice to have him run through the physics of it and what matters and why. And just how we're, when you think about first principles thinking, which is a cliche, but it's a cliche because it's useful, right? There is a limit to what electrical propulsion can do in the face of solar panels that we have today and so on. And there's a limit to what chemical propulsion can do. And he explained that well. And then the only real unlock is this new idea of, can you harness the sun in some different way to do a propulsion where you don't have to send an oxidizer up with your fuel, and you can have fuel that's more readily available across, places that aren't Earth and so on. So that was pretty cool.
That is super cool. And that was also the piece that stuck out to me as well, which was just, there are physical limitations, but if you go with the sort of hybrid approach, or really something that's using a different kind of fuel entirely, whether it's not the electric power that you have on board, it's thermal power from the sun, you can really stay out there for a long time because it doesn't matter what you're actually using as the media to use as propellant. He said we were using ammonia, but you could easily put anything in there. You could put space dust in there and then shoot it out super fast. And so it really is just that rocket equation and us thinking cleverly about conservation of momentum that kind of unlocks the stars. So that piece to me is what it really felt like was different than what I had, than the way I was thinking about it before.
And I love that he brought up the nuclear thermal propellant because, the question becomes, electric propulsion today, it can move you slowly when you're near the Earth and when you're near the sun. But as you get further out in the solar system, it becomes less effective because the strength of the sun is less effective on the solar panels that you need to drive that electrical propulsion. And that will be true of solar thermal as well, but not nuclear thermal, which you can take that anywhere. And nuclear is just phenomenally energy dense.
Yeah.
But you're still unlocking that, high impulse output of the rocket nozzle without having to carry so much fuel around. So that's pretty cool. What we didn't get into, because time is so short and he's in the conference, he's got to do that thing, was this, actually how it works is crazy, right?
Yeah.
You put a satellite up, it unfolds its wings, it collects the sun's energy and dumps it into a heat battery that then stores that up and can jump all around the solar system until it does it again. Man, we could have talked to Jeff for an hour just to get into how the thing actually works. Like put on my popular science, how it works, the cross sections. It's really cool engineering. What's possible now?
It's actually technology that had been developed in, I think, the 90s or early 2000s by NASA. So a lot of these ideas for these architectures have existed for a while, but what hasn't existed is a way to build it such that you can actually get enough heat into it that you can get that ISP and the thrust that you're looking for out of it. And that's what I think people like Jeff have cracked the nut on, and why the orbital economy is going to explode and truly become the final frontier. So,
well, that comment is really, I think, the biggest idea that jumped out about why solar thermal now. If it was an idea we'd had before, probably Leonardo invented it hundreds of years ago somehow. Many of these old ideas are new again, but it didn't work. It worked in theory, but not in practice. So why does it work now, right? And I think it was really fun having you two there. You both were at SpaceX, really pushing the edge of what's possible from a manufacturing perspective to make launch happen. And it's just the next thinking of that to bring it to what else is unlocked by these new techniques: additive manufacturing, AI design for heat exchangers, things where we can take our manufactured machinery beyond what was possible in 1998 or 2005. It's really fundamentally different today. And you touched on this earlier. We're in the middle of deep tech, reindustrialize, build again. And that's true. And it was funny. I was having two thoughts. One is space is really a manufacturing play. SpaceX is a manufacturing company that manufactures rockets. That's why the cost is down. We talked about the Model T earlier. The only reason there's 1 billion cars plus in the world is that we figured out how to make them in a factory incredibly efficiently. And figuring out how to do that with rockets, unlocked space. Well, people like Jeff and the many other people building in this world now are figuring out how to bring manufacturing perspective to the things we put in space. And on that note, most people don't know this, but the biggest electronics manufacturer in the US today, do you know what it is? You probably do.
No, I don't know.
Well, it's kind of you to pretend you don't. It's SpaceX. They're building SpaceX satellites, Starlink satellites. It's crazy, but they're like, you'd think iPhones, but of course we don't make those here anymore, or many other, consumer electronics goods. Well, Elon went and built the biggest electronics manufacturer in the US in the modern era.
Yeah.
And he's cranking out satellites. And that's just the start of this. Jeff is building a factory to crank out satellite propulsion buses and systems. Space tech is manufacturing tech. Deep tech is manufacturing tech. You have to be able to build this stuff at scale and efficiently, and then it unlocks a new world.
That new world is much closer than I actually thought it would be. And I think one of the key unlocks now, as I'm just ruminating over what he said and what you're saying now, it actually might be like refueling stations. We focus so much on specific impulse and how much basically miles per gallon, that's what specific impulse is for satellites, you can get. But that actually doesn't really matter if you have a gas station and enough money to refill your tank. You can kind of go an unlimited distance, which means your whole orbital transfer budget, delta V, goes from being some specific number to unlimited if you can just keep refueling and keep refueling. And that means, in my opinion, one, of course, you get this orbital economy with your gas stations and space exploration becomes more viable. But two, it makes it feel like the key asset on orbit, the key characteristic that you're going to want to have is survivability. Because if you can just stay up there, you can keep taking pictures, you can keep doing whatever you need to do in the defense world. If you can just keep refueling and keep maintaining, I think that's what the real edge is going to be for the companies, both on the commercial and defense side. It's survivability.
Yeah, and that really is the core thesis of why SpaceX works, is we don't just build one rocket, chuck it up in space and blow it up. We use it again. We catch a skyscraper, and Jeff is unlocking that. And I know it's so crazy we don't even put it in the decks when we go raise, but Jeff dreams of gas stations in space, and you just get to do this thing forever. And then you get reusability of these components. So it's not just higher efficiency on how we make the things, which is true today. It's probably a 500x, 1000x, 10,000x improvement in what we can put in space in terms of like capability per dollar.
Yeah.
And then it's cheaper to put that cheap capability per dollar in space. But now we don't have to throw it away in 5 years if you can unlock that.
That's crazy.
It's going to be huge.
It's crazy. Then servicing and repositioning and all the logistics that now are become repeat services because you have this infrastructure become recurring revenue business models, like really investable business models. So I'm really excited to see what happens in the next 10 years. It's certainly part of our thesis for investing in the infrastructure for space economics, but I'm even more optimistic about how orbital assets are going to grow and what it means for all of us.
And that goes back to Jeffen's paradox again. The cheaper and better we get at this stuff, the more stuff we'll do with it. We can't even imagine how big it's going to be. Jeff left us with a comment that we should probably think even harder about what a modern Star Wars strategic defense initiative, there's a bunch of fancy new names for it, Golden Dome and so on, but there's real money going into that. And probably this time it's actually going to work, which becomes interesting. But it's also going to drive research and development further to get even more capabilities in space that we can't even contemplate now. So that's also, maybe for a future conversation, we go find somebody pushing the edge of that forward and ask about space lasers or what's different, brilliant pebbles and smart rocks and all the ideas we had in the past that didn't quite work and probably will now. Or find somebody to talk about rods from God and all the other crazy space ideas.
We're just at the beginning. All right. Well, I think that'll do it for this episode. Clearly, there's so much more ground to cover. Good thing we'll still be around next time, and we'll have a lot more things to talk about in space and across deep tech and across the long frontier of technologies that are going to shape the future of human civilization.
Yeah, Brannon, that was awesome. I really appreciate your catalyzing this. Ton of fun to hear from Jeff. And anybody who's listening, we appreciate you. You folks are all builders. You're the investors, the researchers, the scientists, the curious people. Kids who are listening, especially appreciate that. Anybody dreaming these dreams, you're our people. And the only way the science fiction future happens is if we make it happen. Yeah. And I think this podcast is going to be about finding the people who are making it happen, hearing their stories, digging into a little bit of the history of how we got here, putting some context around it. So we're going to keep going, have fun. We want to hear from you if you liked it.
Yeah.
We want to hear from you if you didn't. Either way, you should share it with someone. So thank you for sticking it out to the end.
Thank you for tuning in for episode 1. We'll see you next time.